Hi guys, this video today is going to be talking about oblique asymptotes. That word oblique, if you think about that word, if you know what your oblique muscles are, they allow you to kind of tilt over, so they'll kind of slant you. Also, if you remember from geometry, you had oblique cylinders and oblique cones. Again, they were things that were sort of tilted over. So oblique asymptotes are slanted asymptotes. That's what they are. So far, all we've studied is vertical asymptotes. Today, we're going to talk about what happens if they're slanted. And also, in fact, this is also going to get into horizontal asymptotes as well. So what I want to do to teach this to you is to use long division. You won't end up having to use long division every single time, but you will need it to help you realize what's going on. Sometimes it'll be actual long division, sometimes it can just be synthetic division, and sometimes it might just be kind of mental math in your head of dividing things. But we are looking at the function as a whole. Just like we do for end behavior. When we look at end behavior, we looked at, okay, what is 2x squared over x, and what would that give me as far as my x goes? And so therefore, that gave us the end behavior. That's going to lend itself to oblique asymptotes and horizontal asymptotes as well. So to do this today, we're going to do it doing long division. So I'm going to have you, I really want you to be doing a lot of this on your own. So I'm going to be kind of going through saying pause here, try it on your own, etc. So to set this one up, you know what, for this one, let's just use synthetic division because we can. Like this is the kind when you could use synthetic division. If you don't remember, the time that you can use synthetic division is what you're dividing by is a linear. That is just an x plus something or an x minus something. So number one, we can just use synthetic. Number two, we could use synthetic on that one also. But anyway, what I'm saying is what I want you to do is start off here. We'll just use synthetic because synthetic because we can. And so we're going to set this up. We're going to go through and we're going to do our synthetic division or long division. I'm going to go through number one with you, but like I said, in a little bit, I'm going to have you doing a lot of these on your own. Okay, I'm going to bring down my 2. 1 times 2 is 2. I add these together. I get -3. 1 times -3 is -3. And over here, I get -6. Now, when I do this, this is going to be helping me find my oblique asymptotes or my slant asymptotes. When I do it, I don't really care about that remainder. Because think about a remainder. Like think about a long division remainder. All that remainder is like a little fraction. It doesn't really make a whole lot of difference, right? It's just a small little fraction. It's so small we just call it the remainder. And so here we are not going to pay attention to that remainder. We're just going to drop off the remainder. We don't really care about the remainder. So our answer without the remainder is y equals 2x minus 3. That is going to be my slant asymptote. I'm going to go ahead and draw that dotted line over here on the side. Okay, while I did that, I also came up with some more information, but let's talk about that asymptote that we were just about to talk about. It starts at -3, it goes up to right 1, up to right 1, up to right 1. I'm going to draw that as a dotted line because it's an asymptote. That is my oblique asymptote or my slant asymptote. I also took a second to factor the numerator and think about the denominator because that denominator, that gives me my vertical asymptote. So I'm going to come over here and put a vertical asymptote at +1. The numerator is going to give me my x-intercepts. So it looks like I have one at -1/2 and +3. Okay, now we need to figure out how to draw this. I think you can kind of see, it has to hit that point. It has to get closer to the asymptotes. So it's going to be, you know what else we could think about before we do this? Is the y-intercept. Do you remember how to find the y-intercept? To find the y-intercept, we plug in a 0 for all of the x's. And so if we plugged in 0 here, 0 here, and 0 here, that would give us 0, and then all we have left is the -3 over -1. Well, -3 over -1 is just 3. So our y-intercept is up here at 3. And so again, I think that even helps us a little bit more even figure out how to go. We're going to get closer to that intercept, to that asymptote. We're going to go through the y-intercept, we're going to go through the x-intercept, and get closer to the asymptote like that. It's kind of bent over like that. And we're going to do something similar over here. We only have one point to go off of, but it's going to get closer to that asymptote, closer to this asymptote like this. Let me show you on Desmos what that looks like. Here's what it looks like on Desmos. I have my vertical asymptote, my slant asymptote. You can see there is my y-intercept, there's one of the x-intercepts, there's the other x-intercept, and it just kind of gets closer and closer. Let me zoom so that we can see what it looks like kind of in the big picture. Okay, it looks a little bit like an X right there, but those X's never touch. Like the black lines are touching because those are my asymptotes, but remember those red lines are not touching. But that's kind of what the long-term graph is going to look like. If I go back to a regular zoom level, here I am back at my regular zoom level. That graph, it has a slant asymptote. And so we're going to talk a little bit today about end behavior also. So it is going towards negative infinity and up towards positive infinity, but just kind of in a slanted way, not a straight up way. Another thing to think about is where is the graph and where isn't the graph. And so when we talk about these, we have to have something in each section of the graph. But when I say each section of the graph, I'm only talking about from left to right. And so what I mean is my vertical asymptote is kind of my dividing line here. I have to have something to the left of this vertical asymptote, and I have to have something to the right of this vertical asymptote. These little V portions, sometimes the graph will be in there, but sometimes it won't. It just depends on your end behavior of your asymptote. Remember, this was an x minus 1 to the first power. Since it's the first power, it's opposite ends of that vertical asymptote. So it's potentially could have one up here instead, but it was an odd asymptote. Anyway, I just want to tell you that there has to be something in each section, but when I say each section, I'm really talking about left of the vertical asymptote and right of the vertical asymptote. Okay, let's go back to our notes. That is number 1. That showed us how to go through, graph the vertical asymptotes, learned about the slant asymptotes, and fill in the graph. Let's try number 2. Okay, once again, since it is just a linear, we could just do our synthetic division. So we'll set that up. Here's what I want you to do. I want you to finish that synthetic division, and I also want you to see how does this factor, because that's going to help you graph it. So let's do those two things, synthetic division and factor it, and see where you can get with that. Okay, we do the synthetic division, we get x plus 3. That x plus 3 is going to be our slant asymptote. So there it is. X plus 3 means it starts at 3, goes up 1, right 1, up 1, right 1, up 1, right 1. We also have the vertical asymptote at negative 5. Why did I put that there? Okay, so sorry, I had the asymptote in the wrong place. There's my asymptote at negative 5. And then my x-intercepts, that's what I had wrong before. My x-intercepts, I have an x-intercept at negative 10 and another x-intercept at positive 2. If I look at my y-intercept, I plug in zeros for x's and I get negative 20 over 5, which is 0, negative 4. So my y-intercept is here at negative 4. So again, I think we can figure this out, but I'll go ahead and show you what this is supposed to look like on the graph. Okay, so here we are on Desmos. We have our vertical asymptote at negative 5. We have our oblique asymptote at x plus 3. And these two, this one hits at negative 4 and positive 2. This one hits at negative 10. And so we have these two portions. Once again, we have something in each part of the graph. And by part, I mean being divided by that vertical asymptote, not being divided by the oblique, just divided by the vertical, that we have something in the left-hand portion in this case, something in the right-hand portion. So let's go back and draw that on our notes. These are not always easy to draw. Mine are not very attractive here. The main thing is you are getting closer to the asymptote, the vertical asymptote, you're getting closer to the oblique asymptote, you're getting closer to the oblique, you're getting closer to the vertical. So that's what's going on. That's why in Desmos I think it's helpful because you can zoom in and out so easily. But that's what's going on there. We have two cases of an oblique asymptote. Let's take a look at number 3. Okay, with number 3 here, we have a couple of new things going on. One thing is, I don't know if you can tell there's a GCF. So maybe we should simplify first with our GCF. And in the denominator, we also have the GCF. So that then factors down to x plus 3x minus 3, which is going to give us our vertical asymptotes. However, the numerator, although you kind of think maybe it can be factored, it actually cannot be factored. And if it can't be factored, that means we maybe would have to do the quadratic formula to find our zeros. But let's just not do that yet. Let's just kind of go with what we have, okay, before we get there. Let's just put that on hold for a minute. Now, what we do need to do is we do need to do our long division. So I'm going to set up my long division. All right, so I've set up my long division. I had to do long division because it's not a linear. The denominator has a quadratic in it, so I have to do long division. I have to include my 0x. What I'm thinking is how many times does 3x squared go into 2x squared? Or in other words, another way to say that is 3x squared times what would give me 2x squared? And that's kind of a strange question because the answer is a fraction. And it's a fraction without an x, right? It's just 2/3. Because if I took 2/3 times 3x squared, my 3's would cancel, I would get 2x squared. And then my next term is a 0x, because 0 times anything is 0. And then my last term is 18. And so I go through here and I start subtracting. And 3x squared doesn't really go into, so I'm kind of in a weird spot, right? This is coming out really strangely. I intended it to come out strangely. Here's the deal. What's happening here is y equals 2/3 is the asymptote. It's not oblique, it's horizontal. So this example, number 3, does not have an oblique asymptote. Instead of an oblique asymptote, it has a horizontal asymptote. And so I draw a line at 2/3. Do you see how that's like, I mean, you know, it's not perfect. It's about 2/3 here, okay? That is my horizontal asymptote. My vertical asymptotes are at -3 and +3, but my oblique, I don't have an oblique. And now, when we talk about end behavior is not always positive and negative infinity. We also don't have an oblique asymptote here. What we have is a horizontal asymptote. And so if I ask you what is the end behavior is y equals 2/3. That is, my ends are going to get closer and closer and closer to that line. It's going to be like what we very started out this unit with those kind of L shapes. That's what's going to happen here. Okay, now the problem is a lot of times it's hard to know, should that L be up above or should that L be down below? And sometimes to figure that out, you have to plug in numbers and you just have to see what comes out. So just be aware of all those things. One, we have horizontal instead of oblique. Another, our end behavior is horizontal. Our end behavior is not infinity. It is a number. And then finally, with this kind of action, you're going to have an L shape, not pointing up and down to infinity, but an L shape. Let's put this one in Desmos and see what we get. Okay, here we are on Desmos. I don't know if you can tell. I might zoom in here. It does not have any x-intercepts. It does not hit the x-axis anywhere, and we'll go back and look at that. But that's because that numerator that I said it couldn't be factored, and so we would have to do the quadratic formula, that numerator, when we did the quadratic formula, which we didn't do, but if we did it, it would come out to be an imaginary number. So there are no x-intercepts here. The other thing we wanted to look at is our L shapes. We have this L shape up here, and it's hard to see on Desmos. You know, it's not supposed to be crossing like that. Why is it crossing like that? It's not supposed to be crossing like that. It is getting closer and closer and closer to 2/3. I wonder if I have it graphed incorrectly. But it's supposed to be getting closer and closer to 2/3, and on the other side also getting closer and closer and closer to 2/3. I wonder if what it might do is it might dip down beneath it here and then come, yikes, and then come up later. Well, it's getting close. I mean, that's what an asymptote does, right? It gets closer and closer and closer. Sometimes it crosses. Remember, I started off this unit warning you, sometimes horizontal asymptotes it might cross. Vertical, it does not. Horizontal, sometimes it might cross, which I know is just bizarre. Why does it do that? It just drives us crazy, but it does happen sometimes. But here's what your graph should look like. Let's go back to that paper and graph that. Okay, and then again, the question will come up, how do I know if I should put it up here or down here? My answer is going to be plug in some numbers and see. So for instance, if I wanted to plug in some numbers, I could plug in a -3 and work it out and see what I get. And if I plug in a -3, I should get a positive answer. Whereas if I plug in a 0, well, we can do that easily. If we plug in a 0, 0, 0, our y-intercept is going to be, we plug in a 0 and we get 8 over -27. I don't know what decimal that is, but I know it's a negative number, and I didn't draw mine very well because it should be right about there, okay? So that's going to be where it hits, is 0, -8 over 27. So it's in the negative quadrant, and then your end behavior of this asymptote was a first power, x plus 3x minus 3, to the first. So they're odd and they're odd. So you have enough information that you can do that. But if you don't have enough information, you can always plug in numbers and just make a table of values and see what happens. But the y-intercept is an easy one to get, and then you can go from there. Let's take a look at number 4. Okay, back to kind of strange things happening. Can I divide this? Does that even make sense to divide this? Well, how many times does x squared go into x? What would you have to multiply times x squared to get me x? And wouldn't it have to be 1 over x? And so 1 over x times that is x. 1 over x times the next one is -1. And then we get -6 over x. Kind of strange. But remember, we're not caring about remainders. This answer, when I do my long division, comes out to be 1 over x. That is actually not the asymptote. The asymptote is actually the line y equals 0. And we're going to talk about some general rules here in just a minute. But another thing is, do you see what the x-intercept is? The x-intercept is 0. Bummer, because it's on that horizontal asymptote, and that just confuses us, but it's going to work. Our vertical asymptotes are back to -2 and +3 again. Let's go to Desmos and see what we get. Okay, here's what we have on Desmos. We have that intercept at 0, 0. Annoying, but that's how it happens. We actually, look what's going on. We have this kind of a bend in a way. It's not a bend though. It's going straight through. It just had to do that because it had to get from this asymptote all the way over to this asymptote, so it had to make a hard right. Again, we could plug in numbers to find out, is this supposed to be above or below? Is it supposed to be above or below? And we could end up getting the right graph. But seeing it here on Desmos is going to help us for today. So here we have it on Desmos. Let's go back to our paper. Okay. So here is our graph. The end behavior is y equals 0. It's not infinity. It's going to the side. It's those L shapes. And that's what happens when we get this, when we divide. Yes, that is what we got when we divided, but what we were really looking for is, how about those asymptotes? That asymptote means that the asymptote is y equals 0. Our horizontal asymptote is y equals 0. One last one to do here. And so once again, we're going to set up our long division, and we're going to see what happens. So we set up our long division. X squared goes into x to the 4th. It goes in x squared times. So if I distribute this out to the side, I get x to the 4th minus x to the 3rd minus 6x squared. I'm going to subtract this, which gives me a 1x to the 3rd plus 6x squared. I'll bring down my 0x. That means I'm going to get an x here, running out of space. So that's going to be x to the 3rd minus x squared minus 6x. I subtract, so that drops off. This is a 7x squared. This is a plus 6x because I'm subtracting. So now that goes in 7 times, and then I get a remainder. Okay, so my long division has yielded me this equation. Okay, asymptotes actually don't make parabolas. That's not possible. So that's what I got from the long division. That's true, but that's not my asymptote. What this means is there is no oblique asymptote and there is no horizontal asymptote. Instead, I have end behavior going to positive and negative infinity. So it's like the old-fashioned kind where it's just going to go straight up, straight down, whatever. In this case, both sides are going to go up. Again, my vertical asymptotes are going to be at -2 and +3, and I don't have a horizontal or an oblique asymptote, which is fine. You don't have to. And then lastly, I want to talk about that x to the fourth. That means I'm going to have a 0 there at x at the 0, 0. And it is going to be a bounce. And the fact that it's x to the fourth is probably going to make it a little bit wider than an x squared. That's what's going to happen. Let's look at it on Desmos again. I had to zoom way out for you to see it because they're all the way up here at, I don't know, 49 or something, 41. And so that was hard to find. But look, remember how we said the end behavior was positive infinity, positive infinity? It's definitely going straight up to positive infinity. And it does have these vertical asymptotes. I can zoom in a little bit there so we can see what's going on. It also does have an intersection point at 0, 0, so that is there. See how it's a little bit wider or flatter than a regular x squared? That's why the x to the fourth, that's what the x to the fourth does. And finally, we have some piece in each section of the graph from left to right. Our vertical asymptotes, we have this little floater up here. We have this piece down here, which is attached at the 0, 0. And then we have another floater way up there at the 40. Let me try to zoom. There we go. Out there at the 40 something. So I'm going to go in and graph this, but with the graph paper I have on your paper, it's counting. You know, it has boxes on it, and we're not going to use that aspect of the graph paper for now. But let me show you what I want you to draw. Okay, so we had this middle section that was touching the 0, 0, but staying within the asymptotes, and then we had 2 floaters over here on the 2 sides. And so there's our graph. Okay, let me just review for a second here. What I was trying to get to with this lesson is the way you know what the asymptotes are is you do division. The horizontal and oblique asymptotes come from division. Synthetic division if you can do synthetic division, long division if you can't do synthetic, then you do long. And those give you your oblique asymptotes or they give you your horizontal asymptotes. That is the way you do it if you don't want to memorize it. If you want to memorize it, on the back of this paper, I have what you have to do to memorize it. Okay, if you are better with memorizing, and maybe even you kind of need a little bit of both, because honestly, this needs a little structure to it. Here's what you have to memorize. If the numerator is greater than the degree of the denominator, the degree of the numerator is greater than the degree of the denominator, then the horizontal asymptote is the leading coefficient over the leading coefficient. I'll look at an example in just a second. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is y equals 0. And that's when you think 1 over x. That is, the numerator is less than the denominator in the degrees. If the degree of the numerator is equal to the degree of the denominator plus 1, that plus 1 is important. That's when you use long division. That's the only time you use long division, is if the numerator is equal to the denominator plus 1. In other words, the numerator is greater than, by 1 degree, greater than the denominator. That's when you use long division. If the numerator is greater than the denominator, then you use the old-fashioned plus and minus infinity and behavior rules, the ones that we've been doing before, the ones that you're familiar with. Let's take a look at 4 examples and how those play out. So take a second, look at these 4 examples, and think of which one is which. You might even pause it here to see which one is which. Okay, if we look at these 4 examples, the first one is the numerator is 1 degree higher. When it's 1 degree higher, that's when you use long division. That's going to give you an oblique asymptote. This one, the denominator is 1 higher. If we reduce that, it would give us 1 over x. 1 over x means you have a horizontal asymptote at y equals 0. Number 3, they have the same degree. They're both x squared. What that means is we look at the leading coefficient, the 4 and the 2, and we reduce that down to 2. So this one has a horizontal asymptote at y equals 2. In the last case, we have x to the 4th over x squared. That means if we did divide it, we would get x squared. That means that we have that positive and negative end behavior. So just to clarify, end behavior is no longer only positive and negative infinity. We have these other options. And if it's a horizontal asymptote, then we're going to have these kind of L-shaped things, right? The things that look like this, if it's a horizontal asymptote. And so that now is our end behavior. It does not go up. This would go up. Horizontal asymptote means it doesn't go up to infinity anymore. It gets closer and closer to that 2. If this one were to match up with there, it would get closer and closer to 2. Okay, that is a lot for one video, and we will obviously do some examples of this tomorrow.